All right, good afternoon. We're going to talk today about conditional probability and independent events. So, simply conditional probability is two events that the probability of the second event changes because of the occurrence of the first event. For example, if you have a deck of cards and you draw two cards, say the first one is ace. Well, when you draw a card, that the card reduced, or the number of cards reduced by one. So when you draw the second one, you have already 51, not 52, because you already drew one card. So now the probability changed. We're going to talk about this idea in depth in this section. But for independent events, think about rolling a die and tossing a coin. If you toss a coin, the probability is 1/2, and getting a head is 1/2. Rolling a die and getting number 2 is 1/6. They do not change each other. So because of that, we call them independent events. Okay, let's go in depth here, and we want to know the conditional probability. Okay, so if we start here, so an example, we have three cities, and these three cities have played the host to in Summer Olympics and games in 2020. If these three cities have the same team, and each team has equal chance to win. So if we have three teams or in three cities, that means that each one has equal chance, which is 1/3. So this is the probability. But if I tell you that a city B decided to pull out of the contention for any purpose, now the probability changed because I have two teams. So the chance for A or C to win become 1 or 2. Therefore, because city B left the competition, city A and C have a chance to host the game is 1/2. That's 1/2. Okay, so let's talk about another example. So let's go back to the two cards. So two cards are drawn without replacement. So this is what I'm talking about here. I did not replace the card. So one card first and then the second card. What is the probability that the first card drawn is an ace? Well, let's write some notes. Well, what do I know? I know that I have 52 cards, right? So I have 52 cards. And I have 4 aces. So therefore, the probability that the first card drawn is an ace is, it's called PE, that the event is drawing ace, is we have 4 aces over the sample size is 52, and this is the probability. So now I know about that. So we can also simplify is 1 over 13. I know that there is 4 aces, and we have the sample space is 52. Okay, so this simple way to think about a simple or one event probability. But what is the probability that the second card drawn is an ace? So now the second one is an ace given the first card is not an ace. Okay, so now I have to think about it. Well, the first card is not an ace. So if I have 52 cards and 4 aces, so not an ace equal 52 minus 4. I have 4 aces. So whatever left in the card are not aces, which is 48. Okay, now, the probability that the first card, the probability is the first card drawn was not an ace. Okay, so now for the first one, I still have 52 cards, right? And not an ace, meaning that I have 48 cards that are not an ace. Now, the second event, when we say the second event to two events, and when we say here's the word, if you remember, when we decide that in the classroom, that we look at the word and to the probability that the second card drawn is an ace, given that the first card is not an ace. So we have 48 here over 52. Now, what is the second one? So now I drew a card that is not an ace. Okay, so the denominator is reduced by 1 because I drew a card, right? I drew a card. But did I take an ace? No, so those are not ace. So I still have 4 aces. Okay, and now I compute this probability. So this is the idea, in a simple way. Okay, I hope you understand part B. Okay, what's the probability? C, what's the probability that the second card drawn an ace given the first card was an ace? All right, here, the first card was an ace. I have 4 aces, so 4 over 52. Now, I took a card, and that card is an ace. So how many aces left? Exactly, 3. Over how many cards left? The number of cards is reduced by 1 as well, so times 51, or over 51. So this is, here, this 48, not ace. Here's a 4, ace. This is the 52 cards. It's reduced by 1 when I went to the second event. Okay, here is 4 aces. I took 1, so it becomes 3 aces. I hope you understand this idea. Okay, let's look at the solution here. I'll leave that for you to read it later, but for here, we got the first solution is 1 over 13. And for the second one, we know that the first one is 4 over 51, which is what we got here. And the third one is to get 3 over 51. Okay. So based on this idea, in example 1, we see that the occurrence of the first event reduced the size of the original sample space. So what happened here, because we had 52, okay, when we draw a card, okay, the number of cards becomes 51. So the sample space changed from 52 to 51. Well, that makes sense. So also that happens with the card when we have 4 aces and we took 1 ace out, that becomes 3. So the number of the event also changed from 4 to 3. Well, and so this is what we can call this the conditional probability, okay, is the occurrence, so let's write that down, okay, the occurrence of the first event affects the probability of the second event. Let's see here. We go back here. Reoccurrence of the first one here, 4/52. This is the probability, right? But because we draw card without replacement, this probability, let's give another color, this probability is not 4/52. It changed because these two events are conditional. We're eventually we're going to call them dependent. We talked about that in the classroom, and we're going to go in depth here. Well, let's keep going. So we understand the concept. We call this the second one. So we have two probabilities here. We call this one, the probability. This is PA. But the second one is PB, or the second event, but already I know about the first one. So I'm calling PB, but what I say that, oh, I know A, so given A. And this is how we call it here, PB given A. Meaning that I know something about it. Remember the idea of the three hosts, okay? The probability, so three hosts is 1/3. Each one has an equal chance to host the game. But one of them is out of the computation, so the probability changed to 1/2 because I already given that one city left the computations. All right, so let's go the definition here, or how we do it in simple. Okay, so here is what we go given here. The probability of B given A, and this is what we call it the conditional probability. All right, so let's keep going. How do I look at this by graphs? So consider this experiment with uniform space. Oh, what does uniform mean? Uniform means that all the probability are the same. For example, when you roll a die, you have 1, 2, 3, 4, 5, and 6. Each one of these has a probability 1/6. So they are uniform. Tossing a coin and getting a head. Both of them have 1/2, uniform, and so on. So we consider this and suppose that the events, we have two events, A and B, okay? As we see it here. So we reduce the sample A as in shaded area. So this is how A, and we see the A. So think about A as the four, let's say the 4 aces, okay? So it's reduced by 1 when you draw an ace. Okay, so this is the reduction, reduced sample spacing. Okay, so the second one, so when we talk about conditional probability, again, we say that the second occurrence of the second event, okay, is restricted because of the first event. And we call it, this is a restriction, and because of that, it's conditional probability. So conditional probability, you have to set a condition for the second event because of occurrence of the first event. And because of that, the probability of the second event changes because of the occurrence of the second event. And we call this restriction, or that restricts the element in the set A. Okay. So if we have A, that is because of number of aces change, so the A is reduced. Okay, so let's go with our formula. So we know that P of A and B, we call it A intersect B or A and B, okay, equal P of A, we learned about that before, times P of B. Okay, but if I, that is not conditional, we call this independent. We're going to go through that later in the section. But if they are dependent or conditional probability, then I have P, A and B equal P of A times P of B, but this time given A. All right. And instead of A and B, I'm going to call this, because and I can do the intersection. Okay, it's the same word. Okay. If you solve for B, PB intersect A, divide both sides by PA. So PB intersect A equal that guy, P of A intersect B, over, we divide both sides by PA, so over PA, which is this formula. So if I have A and B, let's look at A and B like that. Oh, like that. A and B. So this is A and this is B. And here is A intersect B. So this is the number, so the probability of B given A is that one divided by P of A, divided by that one. Okay, I hope that it's clear a little bit, and that's what we need for right now. Okay, this is how we get this one. So PB given A, that's the number of the intersection over the number of the sample space. So this is what we know about the probability. Number of the event over the number of sample space. And P of A is the number of the event over the number of sample space. But if we cancel N of S with N of S, we're going to get our formula, which is given here. Okay? Okay, let's take this example. I have a pair of die is rolled. I know that the number falling is here. The sum of the two die is 7. So this is one of the event. I want the sum is 7. And the other event, then one of the numbers on the die is 5. So the second one is one of the numbers is 5. Well, in order to work in this one, I have two events. But the probability, I need the probability that the sum of the number is 7. Okay, so this is A. So P of A. Okay, how can I get the number 7? So I'm looking for, if this A, and given that one of the number is 5, that should be B, then I'm looking for P of A given B. Okay, let's write that A. Well, let's find the probability of A. The probability of A, I have 6 numbers. If you sum them together, you get 7. 6 and 1, 7, 5 and 2, 7, and so on. How many numbers of these? 4, 5, 6. But how big is the sample space? I have 6 for the first die, times 6 for the second one. So the sample space, S or N of S, equal 6 times 6, which is 36. In the first event, I have 6 elements, so 6 over 36. Okay. The second event that one of the die is 5. I have 11 over 36. P of B equal 11 over 36. But now I'm looking at intersection also. So the intersection, if you look at the intersection, you find 5 and 2 is in both. This is one of them. 5 and 2. And also I have 2 and 5. 2 and 5. So I have 2 elements in the intersection. So therefore, the probability of the intersection is 2 over 36. All right, let's see. So here is P, A intersect B equal 2 over 36. Well, again, I'm looking at P, A given B. So if you see in this graph, here is the sum, this one sum of 7. Here, 5. One of the die has 5, and here's the other one. So the horizontal one, the first die has 5. The vertical one, the second die, has 5. But if you see here, the intersection is 2 and 5 and 5 and 2. Well, so I'm looking at P, A given B, using the formula P of A intersect B over P of B. Well, I got the P of A intersect B is 2 over 36. And P of B, we computed here, is 11 over 36. Well, 36 with 36 is canceled out, so I get 2 over 11. And for more details, we are going to find that here. I hope you understand this part. We're going to go even more, okay? As I told you before, we're going to get this, we given this probability, and this probability is from this rule here, this one. We get that probability of B given A is P A intersect B over P of A. We're going to do the product rule. If you divide by 1 and use cross multiply, then PA intersect B equal P of A times P of B given A, which we call it the product rule. So we're going to go here, and we know now what is the product rule. If the two events are dependent. If they are independent, as I explained on the board, P of A intersect B equal P of A times P of B. We're going to look at that later, okay? But this is independent, and this is dependent. And with dependent, we use the conditional probability. Okay. Well, let's get 2 cards are drawn without replacement. I want you to think a little bit about this example. Shuffle from deck of 52 playing card. What's the probability that the first card drawn, let's read the question, the first card drawn is an ace, and the second card drawn is a face card? Well, the probability, we have to get to observe some information. Well, I have the sample size, n of s equal 52. What else do I know? The first card drawn is ace, so I have the first event, n of e, I'm going to call it e, is 4, because I have 4 aces. The second card is face. I have 12 faces, so n of f, I'm going to call this f, is 12. Why 12 faces? For jack, for queen, and for kings. I'm going to call it E and F. The presentation here, let's call it A and B. So we match here. So for aces, I'm going to call this A, and this B for faces. That's instead of A and F, let's call it A and B. All right, so P of A, which is the aces, 4 over 52. P of B, which is the faces, okay, is 12 over 52. Okay, now I want to find the probability that the first card drawn is an ace and the second card is face. Well, then I'm looking at P of A intersect B. Okay, that is equal P of A times P of B given A. Well, I want to make it simple for you. In this presentation, you may see it long, but P of A, we got P of A, 4 over 52, right? Oh, the second one, okay, is faces. I didn't touch the faces. I have 4 aces. I didn't touch any face, okay? But I reduced the sample size by 1. So now I have the sample size here. And I still have the 12 faces, so 12 over 51. If you simplify that, that would be 1 over 13 times 12 over 51. Okay, and that should be it. Or that's it. I don't want you to go through that, okay? It might be a little complicated, but that's it. That is what I want to reach. Okay, so if you look at this one, oh, it looks complicated. You don't have to worry about it. We're going to work in that by examples, and would be easier if you think about drawing 3 cards without replacement. 3 aces, maybe 3 aces. Well, for the first card, I have 4 aces over 52. The second one, I reduced 1 ace and I reduced 1 card from the sample space to 3 over 51. The third one, I reduced again 1 ace and reduce the sample space by 1. So this is an example how you do the probability. So this is exactly that one. Okay? All right, so let's stop by here, okay? And then we will continue in the next video about the rest of that section, okay?